Hello everyone. Welcome to the third episode in my op-amp tutorial series, the Ideal Op-Amp Introduction, Non-Inverting Amplifier, and Inverting Amplifier. If you haven't had a chance to watch the previous episodes, you can check them out on my channel. Today we will be talking about the ideal op-amp. The ideal op-amp is a simplified representation of the op-amp that makes using one very easy, and for many circumstances, a designer does not need to ever consider most of the non-idealities of a real op-amp. Here's the schematic symbol of an op-amp. On the left are two inputs, and on the right is a single output. It also has power supply pins. But when talking about the ideal op-amp, we will not consider the power rails, as they are a real op-amp consideration, not an ideal op-amp consideration. The plus input is called the non-inverting input, and the minus input is called the inverting input. An op-amp is a differential amplifier, meaning that it amplifies the difference between the voltage at the non-inverting input and the voltage at the inverting input. The equation for the output voltage is indicated here, where AV is the gain of the op-amp. Now you might think at this point that you could provide a small signal, either a differential signal into the op-amp or a single-ended signal into the non-inverting input, and ground to the inverting input, and with such a circuit you would be able to get a useful gained-up output voltage of AV times the input signal. However, this is not how op-amps were designed to work, and they will almost never behave well if you try to do this, because AV is designed to be very large, usually at least 100,000 volts per volt, with some op-amps going up to 1 million volts per volt. This makes it difficult to use them this way to amplify most signals, as most signals don't need that much gain. They perhaps need a factor of 1 to 1,000 for most applications. As we'll see, however, this ultra-high gain, along with negative feedback, allows the user to control the op-amp circuit's net gain with some simple external components, so that with the same chip, one can generate a wide variety of gains and circuit properties depending upon the application's requirements. In the ideal op-amp, the gain approaches infinity. Another tenet of the ideal op-amp is that the currents flowing into the inputs are zero. This is important because it means that whatever circuits those inputs are connected to, they will not draw current from those circuits, and thus the inputs serve as perfect, non-intrusive measurement devices. The output impedance of an ideal op-amp is zero, which means that regardless of the load connected on the output of the op-amp will be able to provide enough current to drive it without affecting the output voltage. And finally, we have sort of an honorable mention tenet of the ideal op-amp, that of infinite bandwidth, meaning that the op-amp can amplify a signal of any bandwidth. I say it's an honorable mention because infinite bandwidth is implied by the first two tenets, since we assume AV is always approaching infinity, and thus the input is instantaneously amplified by the op-amp. Even when using the ideal op-amp, we want our voltages to be finite, since in the real world, we will only ever have finite voltages. So, looking back at the first tenet again, the gain and the quantity in parentheses, VOP plus minus VOP minus, are multiplied together, and gain approaches infinity. So what does this imply for VOP plus and VOP minus? This is easiest to intuit with values. So let's assume our desired finite voltage range to be plus 5 volts to minus 5 volts. Now imagine the op-amp gain, AV, is 100. This means that the difference between VOP plus and VOP minus has to be less than or equal to plus or minus 5 volts divided by 100, or less than or equal to plus or minus 50 millivolts, in order for the output to be within our desired voltage range. Now increase that gain to 1000. Now the inputs are within 5 millivolts of each other. Now increase it to 1 million, only 5 microvolts of difference. If we keep increasing it, we see that as this gain approaches infinity, the difference between these two inputs approaches zero. This produces the central equation of the ideal op-amp, that VOP plus equals VOP minus. So, what does this get us? We know that the two inputs have to be at the same value in order for the output to be finite. but we still don't have enough information to actually calculate Vout. The way this equation helps us is with negative feedback in the op-amp circuit, meaning we connect the output pin through some components in a specific configuration back to the VOP- input pin. When we apply negative feedback, we can construct many different kinds of end application circuits with different gains or other properties depending upon the configuration of the components in the feedback loop. This is easiest to understand with a series of example circuits. These equations are all we need to know about ideal op-amps before we can start making circuits. So now, let's take a look at some of the circuits we can build with our ideal op-amp. The simplest op-amp feedback circuit is just connecting the output Vout to the inverting input VOP- and connecting our input signal to VOP+. This is called the unity gain buffer. Using our central op-amp equation, VOP+ is equal to VOP-, and we've connected VOP+ to Vin. And since VOP- is connected to Vout, they are equal. Then, in order to satisfy the central equation, Vout must be equal to Vin. So this produces a simple gain of 1 amplifier. You might wonder, why make a circuit that has a gain of 1? That doesn't do anything. Well, the main reason is to take a signal coming from a very high impedance source, like a sensor or transducer, then make it a very low impedance signal. Notice that the equivalent circuit generating the input voltage shows a source voltage Vs and a series resistance Rs. This is representative of many kinds of signals, from sensors to simple resistive dividers. Recall that in our ideal op-amp, the input currents are 0, which means the series resistance, Rs, doesn't matter, and that Vin equals Vs regardless of the value of Rs. Additionally, recall that the output impedance of an ideal op-amp is 0, so it can drive a very heavy load, and the output voltage will not change as a result of the load. Thus, the output voltage is unaffected by the value of RL. The input signal alone would not be able to accomplish this, as any current drawn by RL would cause voltage to be dropped across Rs. Oftentimes, sensors already output a high enough voltage to use in subsequent circuitry, and so they don't need any voltage gain. All that needs to be done is to buffer that voltage with a circuit that generates a low output impedance version of that voltage so that it can drive the subsequent loads. This is where the unity gain buffer shines. For signals that actually require some gain, we can use the non-inverting amplifier configuration. The input signal is connected to the op-amp non-inverting input, and 2 resistors are connected in the configuration shown between the output and the op-amp inverting input. We've seen this before. It's the configuration I used in the introduction videos with the LM324. Now we'll derive the gain equation from the ideal op-amp tenets. Again, we start with the central op-amp equation, and our input signal, Vin, is again connected directly to VOP+, but this time there's a bit more work to do to derive Vout. Now we look at the implications of IOP-, which just like IOP+, is also 0. This means that R1 and R2 make a simple resistive divider with Vout that is only sensed by a VOP-. So we can construct an equation for VOP- from the resistive divider equation and Vout. And from our central op-amp equation, we know that VOP- must equal Vin, and Vout will change to whatever value that makes that central equation work. So, we can easily construct the equation for Vout by simply inverting the equation we just wrote for VOP-, such that Vout is on one side of the equation instead of VOP-, and finally we substitute in Vin for VOP- here from our central op-amp equation to get Vout in terms of Vin. Additionally, the same high input impedance and low output impedance implications are present in the non-inverting amplifier as in the unity gain buffer. In fact, the unity gain buffer is really just a special case of the non-inverting amplifier where R2 is set to infinity. So here we see that by adding a simple resistive divider, feeding back from the output of our infinite gain op-amp, we are able to set the gain to a finite value tailored to our application by setting the values of R1 and R2. This is a very common use for op-amps, and a simple way to get a precise, well-defined gain. The last op-amp configuration we'll look at today is the inverting amplifier. Note that I've flipped the op-amp symbol vertically from the previous circuit, so that the inverting input is on the top. This circuit has the input signal connected to the inverting input through a resistor, with another resistor feeding back from the output to the inverting input. In addition, we've grounded the non-inverting input rather than connecting it to the input voltage. Note that R1 and R2 are actually in almost the same positions as with the non-inverting amplifier, except with the inverting amplifier, instead of R2 being grounded on one side, it's connected to our input signal. To calculate the output voltage Vout, we need to know two pieces of information: the voltage at VOP- and current through R1. The voltage at VOP- is easily determined by starting with the central op-amp equation and noting that VOP+ is presently grounded. So by the transitive property, VOP- is 0 volts as well. To determine the current through R1, we first notice that, due to the fact that IOP- is 0, the current flowing through R2 and R1 are both the same current, I-in. This introduces an interesting aspect of op-amp feedback called the virtual ground. While VOP- is not connected to ground, and indeed the op-amp's inverting input does not even draw any current, the voltage at VOP- is nevertheless controlled by the op-amp to be 0 volts, regardless of the value of Vin. And as such, we can treat it like a real ground when performing the circuit analysis. This allows us to convert the circuit containing the input signal and R2 into a very simple equivalent circuit consisting of a single resistor to ground. So the input current is simply Vin over R2 per Ohm's law. Now that we have I-in and VOP-, we calculate Vout, which, with a little rearranging, results in the following expression for Vout. Similar to the non-inverting amplifier, the inverting amplifier has 0 output impedance, and thus Vout is unaffected by the value of RL. Unlike the non-inverting amplifier, the inverting amplifier does not have an inherently high input impedance. Rather, its input impedance is equal to the value of R2. As a result, the source voltage, Vs, is not equal to the input voltage, Vin, and thus voltage input signals need to have a significantly lower source resistance than the selected value for R2 in order for R2 to not significantly attenuate the input signal. Now, let's take a moment to examine the properties of this amplifier and compare it with the non-inverting amplifier. Firstly, the gain of the amplifier is negative R1 over R2. The negative means that the signal is inverted with respect to ground. That is, if 1 volt is provided at Vin, then negative 1 volt times R1 over R2 will appear on the output. This can be a desirable attribute, especially when trying to synthesize certain waveforms, or when trying to subtract two signals from one another using a summing circuit. Since a summing circuit can only add signals together in a sum, if you wish to subtract a signal from another, you have to invert one before inputting it into the summing circuit. We will discuss summing circuits in a later video. The gain magnitude is only slightly different from the non-inverting gain magnitude, off by 1. There is one useful difference here, though. The non-inverting gain magnitude cannot be less than 1, but the inverting gain magnitude can be less than 1. One might not consider this to be a very good selling point, as a gain magnitude of less than 1 is not actually an amplifier and can be easily done with a resistive divider. But it becomes far more important if one is attempting to apply gain to some frequencies, but not others, as in a filter. For example, if you put a capacitor in parallel with R1, it would amplify low frequencies but attenuate high frequencies. Such a circuit is called an integrator and will be discussed in future videos. It is also worth noting, at this point, that inverting amplifiers have a very small common mode input voltage range, very close to ground regardless of what Vin is, whereas non-inverting amplifiers have a common mode input voltage that varies just as widely as Vin does. This makes inverting amplifiers more advantageous in some ways than non-inverting ones, though the reasons why are a significant non-ideality and therefore will be discussed in later videos. That concludes this episode. Today we went over the tenets of the ideal op-amp, introduced the unity gain buffer, non-inverting amplifier circuit, and inverting amplifier circuit, as well as derived the gain functions for those three circuits using the tenets of the ideal op-amp we learned. Next time we'll talk about some more application circuits for the ideal op-amp that further demonstrate the versatility of the op-amp. Thank you for watching my video. If you enjoyed it, please like, share, and subscribe. If you have any questions or comments, leave them in the comments. See you next time.